Solutions. This is critical for doing this before you try to do the chemical reactions lab. Okay, first thing we're going to start with is definitions. Solution is a homogeneous mixture. And we talked about mixtures before, and we did mention the fact that this was a homogeneous mixture, and that we would talk about it later. Well, a homogeneous mixture is composed of two things, the solute and the solvent. The solute is whatever dissolves. And the solvent is what does the dissolving. Now, how do you tell them apart? Well, most of the time, the solute is often a solid, not always, so be careful, but it's the minor component. Because you can have solid solutions, you can have liquid solutions, you can have gases. Gases are actually very, very common. There are very few pure. And the solvent, if you're making Kool-Aid, would be the liquid or the major component. Now, the important part is when you look at things, it's a function of what you have. For example, if you go to your medicine cabinets, odds are a bunch of you are going to have isopropyl alcohol. You can find isopropyl alcohol starting at 50%, in which case you just pick a solvent because it's 50-50. But you'll also find 70%, which means that the isopropyl is the major component and water is the minor component, or 91%. Again, isopropyl major, water minor. However, hydrogen peroxide, probably in your medicine cabinet as well, is usually a 3% solution. That means it's 3% hydrogen peroxide and the rest is water. So what is the solute in the solvent? The solute is minor, solvent is major. What that is relative. Okay? And that brings us to solvation. Solvation is when the solvent particles surround the solute particles. And I know that looks like an A. Surround solute particles. And so that's the general term. If the solvent is water, it's the same rule, but it's just knowing that it's water. So if you'll notice here, you have these where the solvent particles are surrounding the particles. Same thing here with methanol. It's being surrounded by water as it's separating. So it doesn't matter if it's two liquids, a liquid and a solid, two gases, whatever. As long as it's surrounded, that's solvation. If it's water as the solvent, that's hydration. Okay, that brings us to the dissociation of salts. Okay, when dissolved in water, salts are going to break up into their ions. Whoops, there. There. Okay, they're ions, which are mobile. And because they're moving charges, they can conduct electricity. More about that in just a second. Now, what's the four-letter word for an ionic compound? A salt. So remember, a salt is the generic term for ionic compound. Now, we're used to using salt to designate sodium chloride in your house. But oftentimes I'll refer to sodium chloride as table salt. Salt is any ion, etc. So here we go. Here's your table salt. You put it in water. You end up with sodium ion and chloride ion. The two things I want you to note. Notice that we went from solid to aqueous. And also notice that we have charges. Because once we split up into the ions, we have to designate what they are. We're back to the oxidation numbers and the oxidation charges, etc. And those are going to come back constantly, etc. Okay, so on the next one we have lithium sulfide, and it's going to dissociate into two lithiums and one sulfide. Remember, this coefficient down here is not part of the compound. So therefore, it tells you the number. So when you dissociate, it comes out front. So this one's going to move out front. Okay, so if we look down at iron 3 nitrate, notice that this one moves out front. There's R3. You can show it here. But this one stays because it is part of the structure. Because you're dealing with nitrate ion. This is one of the ions you were told to memorize. And in case you think that you're safe, it's back. Oxidation numbers are back. Naming is back. Moles are back. Wait, everything's back. Everything builds. So go back through and make sure you understand what we did previously. Okay, so now that you see that sodium is going to dissociate into 2 ions, lithium sulfide is 3 ions, and iron 3 nitrate is 4 ions once it splits up, okay, then we can look at what we're actually talking about. Well, we said that ions, because they're mobile, conduct electricity. So these are electrolytes because they conduct electricity. So a strong electrolyte is a good electrical conductor. And that means it's going to dissociate completely into ions. So if it forms ions, then we're good to go. The soluble salts, more about that in just a second. Strong acids, there are 6. I'll give you a list. The strong bases, again, there's a list, which are basically group 1 and 2 hydroxides. And then 2 other ones, oxides and hydrides, but again, they're on the list. Actually, no, those are strong bases, never mind. Those actually qualify as salts, so you're good there. Okay, weak electrolyte are poor electrical conductors. They will still conduct electricity, but not very well. Okay, so these are ones that dissociate only partially. So these tend to be weak acids and bases. This is weak. Okay, and now, believe it or not, these are easiest ones for y'all right now, because if you have an arrow, to a double arrow like this, that means it's going back and forth. That means it's not dissociating completely. That means it is a weak electrolyte. Okay? Okay, non-electrolyte have no electrical conduction. That means there is no dissociation. And this is actually kind of easy if you remember. These are all molecular compounds. And remember, molecular compounds are composed of no ions and all nonmetals. Now, the reason why I say no ions is because ammonium nitrate is all nonmetals, but it's an ionic compound because it's the 2 ions. Okay, so that's one of those tricky ones that pop up. All right, now here is your electrical dissociation conduction. Here is a picture. I get out of a Pearson text, and you see no light, weak light, and it's bright here. So this is a strong electrolyte, a weak electrolyte, and a non-electrolyte in reverse order. And notice that this one's molecular, this one's a weak, and you might not know that, but I would throw that in as so you would know. And this one is a strong. Okay. So I told you that we would get to the list of strong acids and strong bases. Now, before you freak out, these are really not that bad. These three are the halogens, other than HF. HF does not do well, so it's weak. But the rest of them are all strong. Sulfuric, nitric, perchloric, and chloric. So if you notice, all of these are very common ions. So if you look at it, you're like, wait, those are really common ions. But they're all the strong forms, not the weak forms. Like HClO2 is not a strong. Okay, your strong bases, we said here, were your group 1 and your group 2 hydroxides. Okay? And remember, all your ionic compounds, the salts, okay? Weak acids tend to start with H and are not on the strong list. And as I said before, they tend to have the double arrow. Now, do you need to memorize the list? Well, yes, if you want to do well. If you want to think, oh yeah, I got it, I don't have to memorize this, then you take your chances. Because remember, you're not supposed to look at it, anything in your notes, whatever, when you go to take the test. So be careful about what you do and what you don't do. Okay? So one more thing I want you to look at real quickly is that when we talk about ions in solution, we've got to talk about what the species are. So for example, this happens to be sucrose, not that you know that, but sucrose is a molecular compound because there are no nonmetals. There are no metals. It's all nonmetals. So there's no dissociation because there's 1 mole. No dissociation. Okay? It's a non-electrolyte. But if you take 1 mole of KBr, you get 2 moles of particles because you get 1 mole of potassium ion and 1 mole of bromide ion. Because it's a strong electrolyte. Calcium chloride is a salt, so that makes it a strong electrolyte. So when it dissociates, you're going to get 1 mole of calcium and 2 moles of chlorides because that 2 goes up front, so you end up with a total of 3 moles of particles. So 1 mole of potassium phosphate is going to dissociate into 3 because that 3 is going to come forward because that indicates a number, whereas the 4 on the oxygen stays with the phosphorus because that's a phosphate, that's an entity, and you know that because it's in the common ion list. So you end up with a total of 4 particles. So what you're looking at here is as things dissociate, you have to worry about the numbers associated with them. So for this is the definitional. The next set is where we're going to do the electrolysis. No, that's wrong. The equations that you're going to use in the chemical reactions. And it is critical that you watch that before you try to do the problems. Or if you get confused, go do the problems. Okay?